Okay, so let's talk about standard reduction potential. This is kind of the big calculation in this chapter. There's two. This one and doing some plating electrolysis. So we have a flow of current, and we want to be able to tell how much that potential difference is, and so we have to calculate it. We have a whole table of calculations, and you first have to have a balanced chemical equation because you have to have the same number of electrons being transferred. And the electrical potential is the ability of electric field to do work on a charge. And we measure that by sending it through a wire through a voltmeter, and we can measure it. The things that we could do with it that are work would be things like light a light bulb, etc. In the case of your car, your battery is a galvanic cell, and it is used to start the engine. Once you start the engine, the battery is being charged, it is not being discharged. So another thing that electrical potential can do is be charged on your cell phone. When your cell phone or your laptop runs out of battery juice, it's run out of electrical potential. And so that potential is called a cell potential. So here we have a copper silver cell, and the flow of electrical charge in this cell results from a difference in the electrical potentials of each electrode. One of these has to be oxidized, one has to be reduced. If we do not have an oxidation and a reduction, we do not have a battery or a cell. So it's kind of like you can't have a positive charge without a negative charge. You have to have one of each, one oxidation, one reduction. So the driving force of an electrochemical reaction is measured by cell potential. Depending on the nature of the two species involved in that reaction and the concentrations, the cell potential can vary. Standard potentials E0, and that superscript O means at standard temperature and pressure and concentration. In this case, 25 degrees Celsius, 1 atmosphere pressure, and 1 molar for aqueous solutions. If it is a gas, of course, it would be 1 atmosphere pressure. And the units for E0 are volts or millivolts. The small m stands for milli. In your book, table 17.2 is a standard reduction potential table, and everything on that table is written as a reduction. You have to have one oxidation and one reduction. So one of the reactions that you have is going to have to be flipped, and when you flip it, just like in thermochem, you will change the sign of the E0 on that table. Once you change the oxidation or flip it and you change the sign, now you just add those two values together. If that value is a positive number, then it is a galvanic cell. If it is a negative number, then it is an electrolytic cell. An electrolytic cell means I need to put that amount of energy into the cell for it to work. And I do that when I'm trying to like plate silver onto a base metal. So written below, you see in the center of the page Cu solid and a single line. This is called the standard cell notation. We're going to go through that a little bit later. In this case, copper lost electrons, 2 electrons, and so I'm going to flip that reaction from a reduction to an oxidation because I need to have it as an oxidation, not a reduction. Remember, I have to have one oxidation and one reduction. So if I flip that equation, change the sign of it, and now I add those two together, I would get the cell potential. In the book, they do it slightly differently, and I am going to go through it, but this is the way I was taught, and I think this makes more sense for me. So when I add these two together, I get 0.4596 volts. And again, we have to remember when we're doing addition and significant figures, we look at our columns. We know this to the second decimal place, so we round to the second decimal place. So the book tells you to take the cathode minus the anode. I don't like this just because some students struggle with figuring out which reaction takes place at the cathode and the anode. The anode is the oxidation. They both start with vowels. Cathode has the reduction. They both start with consonants. And so you would subtract the reduction minus the one you need for oxidation. To me, it seems like a few more steps, or the steps are in an order that doesn't make sense to me. But if this makes sense to you, use it. So every redox reaction can be split into two half reactions. And so we have zinc and hydrogen, and I put arrows here on those two so that we can identify them, because what is happening is zinc is going to zinc 2 plus, hydrogen is going from +1 to 0. But if you look on the table, we have hydrogen the way it's written, but we don't have zinc the way it's written in this equation. It is reversed. So that's my first clue. This one's going to have to be flipped around. Makes it a lot easier for me if I think of it as, is the equation written the way I need it? So if I then take those two numbers and I flip the zinc one, which is negative 0.76, leave hydrogen the way it is, then I have 0 plus 0.76 and I get 0.76 for the cell potential. You can do it again, like I said, either way. I will accept either. I understand both. It's just not the way I think. So here's going through what I just talked to you about. The only thing new here is that in blue at the bottom, we take hydrogen is a standard hydrogen electrode, and we set that value to 0, and we measure everything relative to that. And so the standard hydrogen electrode is called SHE, and we use that as our reference point. Everything else is relative to that. And what happens on a standard hydrogen electrode is showed here. We have a platinum electrode, and we have it within a porous glass tube. So liquid is allowed to go in and out of that electrode. Gases are allowed to go in and out. And this is kind of what looks like, and you notice they're pumping hydrogen gas into this tube. And this is kind of what how a pH electrode works. So on that surface, hydrogen plus atoms are adhering to the metal surface. They come very close together. They each gain an electron from the metal, and they form hydrogen that's neutral, but then they bond together to maintain a neutral surface. And so it makes the atom more stable if it's H2 rather than just H. So, like I said, you can take the cell potential, cathode minus anode, or you can do it the way I do it, where you take the oxidation reaction, which would be loss of electrons, zinc, and flip it to get your cell potentials. So, tables of standard reduction potentials have been prepared. They are in table 17.2 or appendix L. Some of them you'll see written out a little differently. Just do your best to find them. If you can't, let me know, and I can send you another page that's maybe a little easier to read. Here's some examples, and I never include water or hydrogen when I'm writing my half reactions. I do that after I balance them. And I have some videos already prepared on that you should watch. I'll make sure I add them to our playlist. So some more cell potentials, and we will start with the Nernst equation on our next lesson, which will be next week. Have a great day.